Swayam Prabha, Digital India, Educated India.
The carrier consultation, the equilibrium carrier consultation, then how the carriers are generated. So what is a different mechanism for generation, such as band-to-band generation through optical photons, or through thermal, or through injection, right? Or injection is of course another mechanism, or trap-assisted recombination. So then Auger recombination. So different mechanisms that we have discussed, right? So one important aspect is which governs the semiconductor, the device properties, how these carriers are going to move, right? So you cannot operate a semiconductor device under equilibrium. So it has to be operated by creation of charge, right, and the transport of the charge, right? You have to somehow inject or create a charge and then transport the charge. So there are two things for any device to operate. The charge has to be created or injected in some way, and then it has to transport. So first part we have already discussed, right? How the generation recombination take place. The second is the transport, right? So transport, there are various mechanisms. So first of all, in equilibrium, this equation Np equal to Ni holds, right? So for N type, this N will become the doping concentration, right? Under certain temperature range, right? That we have already seen. So at low temperature, there is a carrier freeze out. At high temperature, Ni is quite large. So it again becomes intrinsic. So this N equal to Nd is valid for certain temperature range from T1 to T2, right? Then if somehow extra carriers are injected, then system try to restore, right? So where recombination is proportional to Np minus Ni square. Now this expression we have got from trap-assisted recombination, right? So for direct band gap, you already have this Np minus Ni square, and these are not there. So the case of transport is basically the movement of carriers, right? So that movement of carrier takes place when you apply a force, right? So that force, application of force moves the carrier, and which actually disturbs the equilibrium. So if there is an electric force, we call it drift, right? Can you recall what is the force on electron? Q times E plus Q times V cross B. So Q is minus, so you can have minus E here, right? So this is an electric force, this is a magnetic force. So both the forces actually drag the system away from equilibrium, right? And they apply force in certain direction. Of course, for electric field, it is along the field direction, right? For magnetic field, it is transverse to the field and the velocity, right? So this movement of carriers due to electric force is called drift. Then it could also be due to the thermal forces, right, or the concentration gradient, and that mechanism is called diffusion. So high concentration to low concentration, carriers will move. Now, considering these two forces, right? But since we are operating a device at certain temperature, right? If room temperature if you consider room temperature, then temperature is 300 Kelvin. So at 300 Kelvin, these electrons already have certain velocity, right? And that is called random thermal motion. So you can see here, it's a basically random scattering. So if there is an electron here, it will go in certain direction, and there is another atom or impurity, it gets scattered. it hits another impurity or atom, again get reflected. So net movement of these carriers under random thermal motion is 0. So there is no current, right? So I or J is 0, right? So as we know, J is Q times V, right? Times N. So we need to calculate the carrier concentration. So we already know the band structure, and from the band structure how to calculate the carrier concentration. So that can be done. Then we also need to know the velocity. So velocity, of course, will depend on the applied field or applied force, right? So electromagnetic field, right? And charge is of course constant. So what will happen? These carriers will be accelerated by the field, right? But if you accelerate these carriers, the velocity will keep on increasing, right? So what is the mechanism that restricts the velocity, which limits the velocity? Means you cannot go on increasing a velocity, right? So when velocity increases, right, the scattering events become more frequent, right? Let's say at every distance you have one atom, right? And if a particle is moving at certain velocity v, if you increase the velocity, it will quickly cover the distance, and the scattering will be more frequent, right? So that scattering will limit the velocity of these carriers. So what will happen? This applied force will actually give a fixed velocity called the drift velocity. Now, even without the application of field, these charge carriers are moving due to thermal energy. So if you have 3 degrees of freedom, then kinetic energy of these electrons will be 3/2 kT. And if you equate half mv square is 3/2 kT, you get thermal velocity of the order of 10 raised to power 7 centimeter per second or 10 raised to power 5 meter per second. So typically, the mean free path. Now this is mean free path. Okay, mean free path. Now mean free path is a distance an electron travel before colliding or before next collision. So this is, let's say, collision 1 and collision 2. So distance it has traveled before the next collision is called mean free path. So this is basically measured, and it depends on different crystal. And then if you compare this thermal velocity and the mean free path, so lambda by v thermal, right, will give you the collision frequency, right, or basically mean collision time. 1 over tau will be the collision frequency, right? So collision time is lambda by v. So it comes out to be order of picosecond. And if you take inverse, then collision frequency will be order of terahertz. So this is a random thermal motion of the carriers. So you notice here the velocity is already quite high here. So the thermal velocity is already quite large here. Now, when we apply the field, these electrons get some directed velocity, right? And that mobility is basically defined as the ease with which electrons and holes can flow through the crystal. So if there is less number of scattering, or lambda is large, or tau c is small, then what we have, we will have less number of collisions, right? Less amount of scattering. So then of course the mobility will be more, right? So let us discuss this term. Now in the random thermal motion, electrons are already in random thermal motion. Let's say we apply a field. So when we apply electric field, let's say field is in x direction, right? So force on electron will be minus q times ex. So force will be in minus x direction. So these electrons, of course, they will go through the random motion, but overall they will have a component in minus x direction. For example, Oh, I've shown it x direction. So then field should be in minus x direction. Okay. So either way, so if field is in x direction, then electrons will move in minus x direction. If field is in minus x direction, then electron move in plus x direction, right? So you see here, it is again the random motion, but overall it has a component in x direction, right? So what we can write, force is equal to minus q times E, right? Now there are n such electron, so you can write minus nQe, right? Minus q is the charge on electron. The force is basically rate of change in momentum, right? So it becomes dp by dt. So this is a relationship. So due to this force, the momentum will keep on increasing, right? Or p you can write for x direction, because here we are assuming that field is in x direction. So px you can write m times vx, right? So that means velocity will keep on increasing, right? But due to scattering, okay, let us understand what exactly scattering does. So any electron which is coming here and getting scattered, so it has, let's say, uniform probability of getting scattered in all directions, right? So that means if you consider n number of electrons, then the average velocity after the collision will be, if you take the average of this thing, it will be 0. You understand? After the collision, the average velocity will be 0. That is, individual velocity will not be 0. Individual velocity of electron can be in x direction, y direction, or any random direction, but it is equally probable in all direction. So if you consider the average of all the velocity, it will actually be 0. So that's why when there is no field, average velocity is 0 and there is no current. When you apply a field, then in between the collision, apart from random, this QE force is there, right? Which is directed force. So that is basically a drift velocity. Now, if you can actually calculate the drift velocity by this expression, you will get a small value compared to the thermal velocity. And in that region, your drift velocity is proportional to the field. We call it mu times E, where mu is defined as a mobility, E is of course electric field, and Vt is the drift velocity. Now it is something like this. Let's say you are dropping a mass, right? So the force on the mass is m times g. That is the force of gravity. Now when that mass is falling, the air is basically putting the force on it, right? And this is called drag force, right? So the particle that is the mass that is falling is basically falling in the sea of air. So air will put a drag force. So what will happen? It will get some terminal velocity, right? Its velocity will not keep on increasing. Similar case is there with the electrons in the crystal. So when you apply a force on these electrons get accelerated. But due to scattering, they only get a velocity. They don't get. Okay. So now, if you look at this equation, so from this you can write dp by dt is minus nqe. So your p, how it will change? So p at t plus dt will become minus nq ex times dt, right? So you can take this pt to right side, so it will become pt, right? So your p at t plus delta t will become p at t minus nqe dt, right? So this is basically, now n is number of electron. So for individual electron, you can always write p at t plus dt will be p at t minus q e dt, right? Correct. So this is how the momentum will change with time. Now some of these particles will be scattered, right? So when they are scattered, and the scattering rate is tau, right? So in dt time, how many particles will be scattered? Dt by tau. So dt by tau will be scattered, and 1 minus dt by tau will not be scattered. So this change in momentum will be applicable for only the particle which are not scattered. The particle which are scattered, they will again have zero momentum only, because scattering is isotropic. Correct. So we can write that equation here. So P at t plus dt is written as P at t minus force times dt. Now 1 minus dt by tau is the particle which are not scattered, and dt by tau are the particles which are scattered, and they will have randomized momentum, right? So that randomized momentum is 0. Correct. So if you simplify this equation here, if you calculate dp by dt here, so if you take pt plus delta t minus pt this side, your dp by dt will come out to be, you can write here, p at t plus dt minus pt is equal to minus p dt by tau minus e dt plus e dt by tau, right? Then if you divide by dt, so dp by dt you get basically minus p by tau minus e, and this dt term. So dt is very small, so this we can ignore. So you get this expression here, right? So overall force is basically force due to the field and effect of the scattering. So this scattering is basically the is something like drag force, right? Which neutralize the total force, right? So the electron velocity keep on increasing till the force of this random collision or p by tau is same as the force due to the electric field. So at steady state, dp by dt will be 0, right? So that will tell you that p will be e tau, right? Now p is mb, so m will become e tau by v will become e tau by m. So if you write v is equal to mu times e, so your mu will become e tau by m, right? So your mu will become e tau by m, right? Or q tau by m, right? Now, if you consider this velocity variation with time, right? So now this is little misleading. This figure is little misleading in a sense that electron velocity is never 0. At a given temperature T, electron speed of the electron is never 0, right? It's already at V thermal, right? So electrons are already moving with V thermal velocity in random direction. So the net velocity in particular direction is 0, right? When you apply the electric field, then it basically increases, right? And within certain response time, you have this fixed velocity, right? Called the drift velocity. So basically for electron and holes, you can write this expression. For electrons, it's q tau by m. For holes, it is q tau p by m. Now, tau n and tau p is the basically scattering time, or the mean time between two scattering, and m is the mass. So that also tells you that if mass is more, so this mass is basically the effective mass, right? It's the effective mass. Now there will be a difference. The effective mass that we have calculated for density of a state. Now here we will discuss the effective mass for conduction properties. Okay, so that is coming. So you understand. So mobility is q tau by m. And from this, of course, we can write your familiar expressions. The drift current will be q n mu n times c due to electrons. Drift current density due to holes will be q p mu p times e. And if you define the conductivity, then conductivity is basically nq times mu, right? So if you substitute mu here, you have nq square tau by m. Similarly, conductivity due to holes, qp square tau by m, right? And this rho is the resistivity, which is 1 by conductivity. And if a crystal has both electrons and holes, right, then your overall conductivity will add up. So sigma will become sigma n plus sigma p. Or you can write 1 by rho will become 1 by rho n plus 1 over rho p. So conductivity will add up, and rho will basically inverse of the rho will add up basically to get the overall resistivity. Because see, these two carriers will increase the conductivity, right? So their conductivity will add, right? So resistivity should add as inverse, or like harmonic mean, right? It's basically not mean actually. We are not dividing by 2. They're just adding up. Okay. And the resistance, of course, rho times L by A. So these terms you already know, right? Now, question arises, which mass we should use, right? So that is the name is called conductivity effective mass. So let me introduce that one. Now, can you recall what is density of a state effective mass? Now, density of a state effective mass is basically what we did. We took some kind of geometric mean, right? For example, in case of silicon, right, there were 6 equivalent X conduction band values, right? So what we wrote that M effective, right, for density of a state was, there are 6 values. So M to the power 3 by 2 was M longitudinal, M transverse, because there are 2 transverse directions. So you can write mt times mt or mt square. Then its power 3 by 2, right? So that was a relationship, density of a state effective mass. Because in case of density of a state, we were counting the number of states, right? We were counting the number of states. In case of conductivity, what we are doing? We are writing mobility is q tau by m. So let's say along longitudinal direction, mass is ml. Along transverse direction, mass is mt. So if it is moving along longitudinal direction, your mu will become q tau by ml. If it is moving in transverse direction, then this will become q tau by mt, right? So there are 3 xyz directions, right? So ml, mt, mt. So these 3 will add up, right? So mobility in all 3 directions, you can take the average. So mu l plus mu t, another mu t divided by 3, right? So that will become the effective mobility, right? So you can write now here tau is same, so you can just write 1 by m. So this is mu, right? So mu is proportional to 1 by m is equal to 1 by 3 times mu l become 1 by ml, mu t will become 1 by mt, and plus 1 by mt, right? So this will be your conductivity effective mass. and that is basically the harmonic mean. So harmonic mean is nothing but is a reciprocal of the arithmetic mean of reciprocals. So it is a reciprocal of the arithmetic mean of reciprocals, right? Correct. Is it clear? Now, how the current actually flows? So both the electrons and hole are taking part in the current flow. So if you consider a piece of semiconductor and there is an external circuit here, right? So this is negative terminal. So it will supply the electron and they will come back to the positive terminal, right? So these electrons will basically continuously move, go inside the crystal and come out. So as far as conduction by electron is concerned, it is straightforward. So inside the semiconductor also electrons are there. In the external circuit also electrons are there, right? You have metal wire outside. So electrons will move from this negative terminal to positive terminal, right? What about holes? So of course, holes basically absence of electron, right? So if electron is moving to the left, then holes will move to the right. Now when this hole comes at this contact, what happens? This hole, now hole cannot go inside the metal because metal does not have holes. So what will happen? This electron will combine with this hole, right? So this hole will disappear and electron has come from this side. So now there is one hole less and the neutrality of this semiconductor has to be maintained. So what will happen? One hole will be generated here. So that is electron hole pair will be generated here. So one extra hole will appear here and this hole will disappear. So this is what is actually happening. So hole disappears at one end and appears at another end. So how this hole appears? This electron hole pair is generated, right? So hole moves inside the semiconductor, electron moves inside the metal. So that basically that way actually this continuity is maintained. The concept is clear. So I look some questions are there. Oh, they're not questions. They are just some comments. Does band structure for the circuit occurs mean only band structure? Okay. I will not basically ask those derivations of density of a state in this band structure, but band structure basically means you have to understand how the band structure is formed. You should be able to decode the band structure. You should be able to extract different parameters like group velocity, effective mass, all those things. Right? So go through the band structure slides, and you've already gone through the other lecture, so it should not be an issue. Okay, let's continue. So now, so this is the mechanism of current flow through electrons and holes. Now what happens with temperature? Now there are various scattering mechanisms, right? That I was telling you that we will cover next slide, coming slide. So this tau is basically scattering time. So two basic mechanisms are covered here: lattice scattering and impurity scattering. But there are other mechanisms also, right? There is something called carrier scattering. There is something called defect scattering. There is something called surface scattering. So there are different scattering mechanisms are there. So of course in this course we will only cover two. One is lattice scattering and second is impurity scattering. So lattice scattering due to the lattice atoms vibration with temperature. So at of course T equal to 0, these lattice atoms are basically they are fixed in their position, no vibration, no scattering, and in fact the carrier concentration will also not be there, right? Because a band gap is there, so it will be insulator anyway. But if you increase the temperature, carriers will increase as well as the scattering will also increase. But if you notice here, as the temperature increases, right, scattering increases, right? That means the time between two scattering decreases. So this scattering time actually decreases as temperature increases, right? That means scattering rate decreases, right? So lattice scattering increases with temperature. And that is fairly simple to understand because these atoms are vibrating in their position. If temperature increases, the magnitude of vibration will increase, and now there is a greater probability of electron being uh, affected by these atomic vibrations, right? This is also called phonon scattering. Phonon scattering. So lattice scattering and phonon scattering are basically same. So this is due to lattice atoms, and this collective vibration of lattice atom is called phonon. So it's called also called phonon scattering. Another is impurity scattering. Now impurity scattering, of course, if you have more number of impurity, then scattering will increase, right? Because now there is a greater probability of electron colliding with the impurity. So it increases with the number of impurity concentration, but it decreases with the temperature. Now why? Let's say there is an ionized impurity here, right? An electron is going through. If electron is moving slowly, it will get more time to interact with the impurity and the deflection will be more. If it is velocity is fast, right? It will get less time to interact. So deflection will be less. So that way you can understand it depends on the time the electron spends around that impurity. So impurity scattering is basically found to be 1.5 power of temperature. Found to vary with 1.5 power of temperature. So if you see typical um, mobility characteristic, the mobility is Q tau by M, right? So for phonon scattering, it decreases with the temperature and it's dominant at high temperature. So this is phonon scattering, right? And this is ionized impurity scattering. So if you see it, now this is usually seen at low temperature. Now you notice here, this scattering increases with the impurity concentration. So if you have impurity, then this mobility has already decreased, right? So if you increase the impurity, this has decreased, right? But the slope may change here. Understand? The slope may change here. So for high doping, impurity will anyway decrease, right? But at low temperature, this kind of character may be seen. For example, here you can see the mobility values for silicon with doping concentration. So this is for electron, and this blue is for hole. So electron mobility for it start at 1400 centimeter square per volt second, and if you increase the doping to 1:17 or 18, it goes to less than 200, less than 100, right? So you see there is a range of mobility. Similarly for holes, it starts around 450 and it again goes down to less than 100, right? So this is how the mobility of the electron and holes in silicon vary with doping. Now all these values are at T equal to 300 Kelvin, right? Now how the different mobility combine? So mobility, what will happen? Let's say mu is Q tau by M, right? So mobility is dependent on the scattering time. So if there are two scattering mechanisms, let's say one scattering mechanism takes time tau1, second takes tau2, right? So when both the mechanisms are active, what will be the scattering time? It will be less than tau1, tau2, it will be more than tau1, tau2. It will of course be less than, right? Because now there are two mechanisms. So effective scattering time will become 1 by tau will be 1 by tau1 plus 1 by tau2, right? So this is called Matheson's rule. So scattering rate basically combines, right? So rate is basically sum of rates due to all the mechanisms, right? So it's 1 by tau become 1 by tau 1 plus 1 by tau 2 plus 1 by, so all the mechanisms basically impurity, ionized impurity scattering or phonon scattering or surface scattering or any other scattering mechanism, right? So because mu is proportional to tau, so mu also combine like this, 1 by mu become 1 by mu 1 plus 1 by mu 2, right? So this is called Matheson's rule. So that gives you the overall mobility due to, or effective mobility due to multiple scattering mechanisms, right? So it's already 12:59. We will close here and we will continue our discussion in next class.